Good morning, everybody. Welcome to the Climate Science Center seminar for today. We're honored to have Dr. Rosemary Knight from Stanford University visiting us. She's been a pioneer of using very remote and not so remote sensing to understand the near-surface geophysical environment for many years. She's got a number of colleagues and friends at JPL, and we're really excited to hear her presentation. She'll be here all day. I think all of her slots are full, but if anyone's interested in speaking with her, we'll have a little bit of time after the seminar, although it might mean that Graham and I get hungrier and hungrier waiting for lunch. Without ado, Rosemary.
Thanks very much, and I am delighted to be here. Word of warning, I had serious laryngitis about 2 weeks ago, still getting over it a bit, so I've got warm tea, cool water, so if I have to stop and drink, that's why. Yeah, so I'm going to be talking about harnessing the power of geophysical imaging to recharge California's groundwater, and I use geophysical imaging very broadly. Everything from, what did you call it, very remote, so my satellite, Sentinel-1 data, airborne, and there's the not so remote, me on a UTV in the Central Valley. So harnessing the power of geophysical imaging. Groundwater, just a couple slides of introduction. I use this slide a lot. Tree is not to scale. A slice through the ground. We work on systems that are typically hundreds of meters below the ground surface, which is where our groundwater is, held in the openings in the rocks and sediments below the surface. Groundwater is incredibly important. It's 97% of all liquid fresh water. And we've typically assumed there's an enormous abundance of groundwater down there because we can't see it. We can't see it, so we haven't realized that we have been seriously depleting our groundwater resources. And with climate change and population growth, people all over the world are recognizing the fact that we really need to take more seriously the protection of our groundwater resources when it comes to both the quantity of water that we have stored there and the quality of the water. So I've been working on groundwater for a long time now, and now I'm focused on the Central Valley of California, which is an incredibly important agricultural area, but the amount of precipitation sufficiently limited that there's a large dependence on the groundwater system. And this is particularly the case in the San Joaquin Valley. To get you located, if it helps, there's Stanford. Here's the San Joaquin Valley. And the southern San Joaquin Valley, or the southern part of the Central Valley, the San Joaquin Valley, again, a lot of agriculture, but concerns about water. So what does the geology look like down there? So this is based on an image from Claudia Font. We have the Sierra Nevada bounding this alluvial aquifer system, a thick package of sediments, aquifers, a shallow aquifer, a deeper aquifer, a bounding clay unit, the Corcoran clay, which separates the two. And the mountain range, the Sierras, is incredibly important in terms of understanding the hydrogeology here. Not only is it a source of the sediments that make up this thick groundwater system, it's also a source of much of the fresh water. So the San Joaquin Valley has been struggling for quite a while. This dates back to 1977. Here we have Poland from the USGS, who put markers on the who hasn't seen this slide? Hasn't everyone seen this slide? Oh, you haven't? Oh, good. So this is where the ground surface was in 1925. This is where the ground surface was in 1977. So it's showing this 9 meters of subsidence over those 10 years. And this was from pumping groundwater. It caused that level of subsidence. And I always say I find there are two remarkable things about this image. First of all, that amount of subsidence in those 50 years, but more remarkable, did we learn from this? No, it goes on today. So fast forward to an InSAR deformation map of the Central Valley between January 2015 and September 2019. And up to 1.3 meters of subsidence in parts of the San Joaquin Valley. So these InSAR data, this InSAR image is again mapping out the amount of subsidence that's occurring on the ground surface. And in the San Joaquin Valley, large amounts of subsidence going on. It's going down, 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 a lot of it irreversible. So what's happening down there? The groundwater system, a lot of clay-rich material with sand and gravel channels and a groundwater aquifer that's down now, the aquifer water table level down about 30 to 100 meters below ground surface because there's been so much depletion. And the reason this is a system out of balance doesn't require any fancy math. We simply have water out is much greater than water in. Water out is all the pumping. So even though there's a high level of dependence on surface water deliveries for agriculture in drought years, or just to supplement the water supply in other years, people pump the groundwater system. The water in is recharge. So when I talk about recharge, recharge is that refilling, restoring of the groundwater system. And natural recharge happens, it rains, the water infiltrates below the ground surface, there's recharge of water coming from the Sierras due to the snow melt. So this water out being much greater than water in is causing serious problems in this area. Depletion of groundwater supply, dry wells. Many domestic wells are shallow enough that the water table is now below the depth of the wells. It's having an impact on the connected surface water, so the ecosystems that are dependent upon that surface water are being impacted because of the drawdown in the groundwater level. Subsidence of the ground surface, which is impacting the very infrastructure that's up there moving the surface water around, and it's causing a degradation of water quality. So what do we have to do? Decrease pumping or increase recharge? Well, getting everyone to agree to decrease pumping is not going to happen anytime soon. So there's a lot of focus on increasing recharge. How do we increase recharge? Nature can only do so much. So we need to add to the natural recharge that's occurring. And the term that's used is managed aquifer recharge. So in addition to nature recharging the groundwater aquifers, we have managed recharge. One form of managed recharge is to direct water to an area, spread it on the ground surface, and that water then infiltrates below the ground. California's freshwater history has always been floods and droughts, and what's our freshwater future? More floods, more droughts, it's just going to get worse. So how can we think about coupling these two and come up with some solutions? And the solution that's being proposed is FloodMAR. So managed aquifer recharge that's taking advantage of the flood years, such as the one we've just had, capturing that water, getting it underground to recover from or prepare for the next drought. Where can we recharge? You can have designated recharge basins, shown here, but increasingly growers throughout the Central Valley are volunteering their land for what's called on-farm recharge, or AgMAR. And they are volunteering their land to be flooded at times of year where it doesn't impact their operations, and the water then recharges the groundwater system. There's also considerable enthusiasm for floodplain restoration, where you get multiple benefits of enhancing wildlife habitat and also potential recharge of the system below the ground surface. So enthusiasm for recharge is taking off, with the Sustainable Groundwater Management Act requiring that groundwater be sustainably managed. Many of the plans that are coming in from the water agencies see their path to sustainability being highly dependent upon recharge. Groundwater sustainability plans from the San Joaquin Valley, 43% of the plans include recharge. Throughout California, capital costs estimated to be $3 billion. And why focus on the subsurface? There's all these units flying around, and we declared a new unit this year. It's called Lake Shasta's. So above the ground, the reservoir space, we've got about 9 Lake Shastas. The space we have below the ground, 30 Lake Shastas. So it's really worth figuring out how to do this, getting the floodwater to their locations. So where to recharge? What we want to do is maximize the quantity and rate of the recharge. Because land is expensive, investment in the infrastructure to get the water there is expensive, surface water is scarce and valuable, so you don't want to flood it somewhere and then have it just evaporate. And buy-in from growers is essential. You don't want to move water into an almond grove and have it pond there, and it's going to damage the roots. The trees could potentially topple over in a storm. So we need to find places where we have these optimal characteristics. You flood the surface, but there are pathways, interconnected pathways of sands and gravels that are highly permeable, coarse-grained material that can efficiently move the water from the surface down to recharge the aquifer system. So that's our target, is to find these interconnected pathways, and we also want to understand what's happening once the water gets down to this location, where the water now moves regionally and recharges the rest of the aquifer system. So what do we need? We need a fast, reliable, cost-effective way to find these pathways. So you can go around the Central Valley drilling wells and looking for them, but it's so spatially heterogeneous. What we need is something faster, more reliable, cost-effective. We need to harness the power of geophysical imaging to search for these pathways, our target being these pathways. So, ta-da, geophysical imaging arrives on the scene. One of the most thrilling days of my life, October 27, 2015. I drained my gift account to run this pilot study to test out this airborne electromagnetic technology for groundwater management in the San Joaquin Valley. And this is a proven technology throughout the world. It's used for groundwater exploration, but has not been adopted in California for groundwater management. So this was a great opportunity to do this. So this system, you have a transmitter here. Current goes through this transmitter loop. It sets up a magnetic field which goes below the ground surface. You turn off the current, generates eddy currents. The secondary magnetic field is received up above. And what you're doing, so the Google Earth map is underneath to keep track of where we are. But what you're doing is as if every 30 meters you're drilling down and measuring electrical resistivity to a depth of 300 meters below the ground surface. And these are the kind of data that you can get back. So again, what we're doing with this system is mapping out the electrical resistivity of the subsurface along all the flight lines. Imaging depth depends upon the electrical conductivity. So in California, typically 200 to 500 meters below the ground surface. Horizontal resolution along the lines, about 40 meters at the surface. The vertical resolution degrades because of the physics of the measurement. Near the surface, it's 3 meters or less, increasing to about 50 meters by the time you're at 500 meters. So very good resolution near the surface. You get that depth of imaging, though. Along with seeing what's shallow, you can see deep, although you've lost your resolution. But given that very few wells go that deep, this is the first time we're actually seeing into these groundwater systems. What we really want to do is not map out electrical resistivity, but map out sediment type. So how do we go from electrical resistivity to sediment type? We've developed a way of using driller's logs, and we're now trying to fly as close to a well as you possibly can without encountering interference from your power lines. And so you know, at this location, my driller's log tells me that I've got mixed coarse and fine, clay, sand, and gravel, and I actually know the resistivity measurement there. And then you go to another location. You know what's there, you know the resistivity that you measure, and we set up this system of equations, basically forward modeling, accounting for the measurement and saying, over this package of materials, this is the resistivity I measured. You set up your 500 equations, use bootstrapping, and come up with the link between resistivity, which is what I'm measuring, and the sediment type that was there. So above the water table, our sand and gravel had resistivity values in this range. Our clay had values in this range. So I can go from resistivity to sediment type. The water table has a big impact on this transform because water impacts resistivity, but the dominant thing we're mapping out below the water table is the sediment type. Sands and gravels are more resistive, clays are more conductive, and then we have this mixed unit in between. So by using our well data, we now have a way of taking this remarkable opportunity to map out electrical resistivity and get information about sediment type. And what we often do is transform the data so that we're going straight from resistivity to the percent of coarse-grained material. So resistivity values down here, you know you've got mostly clay. Resistivity values up here, you've got 100% sand and gravel, and then some variation in between. So doing that, we can take our airborne EM data and get images like this. So this is along the flight lines, and we're seeing 400 meters down below the ground surface. This was a 20-kilometer line. I didn't have enough money to fly any more than that. And you can see the dark red, the resistive, is sand and gravel dominated. The low resistivity is clay rich. And what this can do is help us start to identify what the pathways are between the surface and deep within the groundwater system. So after acquiring data such as this, I talked to water agencies, talked to everyone, like, we have to do this in California. I wrote a white paper to the governor's office in 2016 with Paul Goslin, who was then in Butte County, and Graham Fogg at UC Davis, saying, we have passed the Sustainable Groundwater Management Act in 2014. We don't have a chance of getting there unless we start adopting some advanced technologies. Drilling wells everywhere, we're never going to get there. And so we laid out a map. Jesse Cruz drew all these flight lines. We figured out what we should do for a reconnaissance scale study. We covered the groundwater basins. It ended up being 20,000 kilometers, $10 million. We said it's going to take you 2 years. $10 million might sound like a lot, but that's only the cost of 60 monitoring wells, or it's the cost of only 60 monitoring wells. DWR came back, said, we're intrigued, but how would we actually do this? So we ran a 2-year pilot project, Soggy and NOAA, key players, many, many partners. We developed and demonstrated the workflow. This is all you need to do, and I'm thrilled to say DWR did it. So in August 2021, they launched this study. They have spent $13 million. They've acquired 27,000 kilometers of data. And December 22nd last year, they released the data in the Central Valley. Look, isn't this phenomenal? So these are the flight lines, all the flight lines and all the fence diagrams. And if I hadn't deleted 20 slides because I realized this was going on far too long, you would see depth slices. So you can go to the Central Valley and you can scroll. Why does this stay on? I'll click it over here. You can, oh, that was wrong. Uh-oh, how do I go backward? And you can scroll down, strip away, understanding what's happening in terms of the subsurface groundwater system. And so when we come back to this question of where to recharge, one of the things we want to do is to tap into, I talk a lot about the natural infrastructure. So we've got our engineered infrastructure all above the ground surface that moves water from reservoirs to aqueducts to irrigation canals to irrigation ditches. Let's just tie nature into that picture at strategic places where we can get the water below the surface. And so again, our targets, interconnected pathways of coarse-grained material. But these come at many scales. And Graham Fogg at UC Davis has been talking about true opportunities for recharge in the Central Valley for about 15 years now. And these are massive paleovalleys that were formed at the melting of the last glacier, the end of the last ice age, massive paleovalleys along the eastern edge of the Central Valley. And so what we decided to do was to see if we could find them with the airborne electromagnetic method. So how these valleys were formed, we went to the Kings River alluvial fan. Here's the current Kings River. But when the glaciers melted, they carved this valley out into the sediments that had been deposited in the Kings River floodplain. And because of the velocity of the meltwater, deeply carved valley and also packed full of coarse-grained materials. So this is this feature that booms out from the Sierras into the Central Valley, dives below the surface, and is packed with coarse-grained material. This is where we went. The alluvial, Graham called them incised valley fill deposits, had been mapped out in this location. And this was done by Graham Fogg and his student Gary Weissman. Why does this? Okay, who can tell me how to get that off without going forward? Never mind. Mapped out where this deposit was, and what we wanted to do was to fly back and forth. So here are flight lines. We had some widely spaced out here, but basically high density flight lines, because what we wanted to see was, can we find this? We know it's there, but this will be the first test to see, can we find these massive paleovalleys with airborne electromagnetic data? Because if we can, then we can look for them elsewhere in the Sierras. Graham predicted that we should find them associated with all the major rivers, or most of the major rivers that come into the valley. They'd mapped one, so we went there. I have to pause, huge acknowledgements. This would not have happened without many, many people, the funding from the Moore Foundation, Ted Ash, who coordinated the acquisition of the data. Then my local partners, managers from a number of the different water districts, people were out there putting instruments in wells, getting water level measurements during the survey, and it was a really great experience. This is the airborne EM system, flying over the Pine Flat Dam on the Kings River, and to show you the quality of the data that came back. So I've kept, the punchline is hidden. So here we are in the south. These are data along our airborne EM lines. The color scheme here, so very resistive is the pink bedrock of the Sierras, and we're seeing 300 meters below the ground surface, and you can see a lot of clay adjacent to the Sierras here. As you come out into the valley, what you see is a green color, and that's because there's a lot of fine-grained materials mixed with coarse-grained materials. So you're mixing blue and yellow, and you remember when you mix blue and yellow, you get green. So we're not resolving those individual packages. It's telling us there's a lot of fine-grained material with coarse mixed in. Well, when we go to the north, there it is. This massive feature that just booms out of the data, highly resistive feature coming out from the base of the Sierras. This is exactly where, this is where they said it would be. And we found this feature about 40 kilometers long, a few kilometers wide. And this is an incredible location for recharge. And more importantly, there are other locations like this. And we know we can now find them with airborne EM data. And looking at a line from the Sierras moving out into the valley, here's the bedrock, and here's where it comes to surface, and then moves out into the valley, diving below the surface in many locations. But this is an example of one of those features where you find where it comes close to the surface, you can move your water to that location, and then the natural infrastructure just transports that water deeper within the groundwater system and laterally. Because this is the shallowest of these features that we mapped out. But you can see evidence of other very resistive, coarse-grained features deeper in the section. And looking at a slice along in this direction, again, here's the coarse-grained feature we're mapping out, and coarser material at depth. So our airborne EM system is mapping out resistivity. Because resistivity is linked to sediment type, we can use it to map out where do we have coarse-grained material that we can use for recharge. And super exciting result of this project is we definitely can use airborne EM. So we don't have to have Graham and his graduate students drilling wells and taking core samples all along the front of the Sierras. With sufficiently high density data such as these, we can find these features. So tapping into the natural infrastructure. So yes, we've got airborne EM, and it can allow us to map out these coarse-grained pathways. Not just do we use this, we don't just use this to look at these massive features like these paleovalleys related to the end of the last ice age, but we also use them to look at a smaller scale. But when it comes to the really small scale, like a recharge basin or almond grove or a floodplain, it's overkill. It's too big, too expensive, and not sufficiently high resolution in the near surface. So we use a towed system. And this system was built in Denmark by the same group that built that system. That's called SkyTem. This is SkyTem, so it's a time domain EM system. This is called TTEM. It's a towed time domain EM system. And it allows us to have the capability of this airborne system on the ground and map out what's below the ground surface. So once they had an early version, it's a bit of duct tape and bungee cords at this point, they came over to California. That was Esben, who was one of the developers. We flew it out to the Tulare Irrigation District to see if we could use it to map out potential recharge pathways. So there's the transmitter at the front and the receiver at the back, and it fits perfectly. You would think someone designed this for looking for recharge pathways in almond groves. I had people make measurements about 30 times before I paid to fly. Are you sure it's going to fit? I don't want this jammed in a row of almond trees. So you can acquire data as you drive then between the rows of almond trees. This was an early version, needed some help in terms of turning radius. Recharge ponds, fantastic for driving around a recharge pond, figuring out where are the optimal places for recharge, and it's just a system that's now getting a lot of use in California. Because what can you do with it? We don't have driller's logs, we don't have wells nearby, but we use cone penetrometer testing, which is a system that uses a large truck and pushes into the ground rods with cone-shaped tips that make measurements that give you information about the sediment type that's there. And using that, we can convert our resistivity data to fraction of coarse-grained material. And so here's a slice. Here's the rows of almond trees. This is a slice through our data. And you can see, you can go to a location like this and you can say, this is actually a really good place for recharge because there are pathways available down to the water table. So in Tulare County, where we did this test, we bought one of these systems. We shared the purchase with Tulare County. And they now have growers wanting to use this system to assess their land prior to recharge. So we now have 2 time domain EM systems that can really help us decide where's a good place for recharge. It's mapping out the sediment type, and what we're looking for are pathways of coarse-grained material. But you've seen the data that we have. We have 27,000 kilometers of data. We have towed EM data being acquired in many fields. We can't sit there and scroll through with various visualization packages looking for these coarse-grained pathways. So the question we addressed, and this work was led by Carissa Pepin, is how can we efficiently find the coarse-grained pathways? So what we've done is to complete the computational workflow to go from the data to an assessment of recharge sites. And what we've done is to say you can start with either basin scale data or local scale data. So you could have your data from a region in the Central Valley acquired with the airborne EM system, which is a larger scale, or you can have data from your almond grove. You use either your driller's log or your cone penetrometer testing to convert it to percent coarse-grained. And so you get images such as I've been showing you. So now what do we do? How do we get efficient with those? And there's been a real rush to think about how we can develop groundwater models or vadozone models. How can we take these EM data and use them to parameterize very complex models of how water moves in the subsurface? And I keep saying we really don't need to go down that rabbit hole. There is so much we can do by interrogating the data space and thinking about what question are we asking? So how can we be clever and develop just the algorithms we need to answer that question? And what we want to know is, where are there fast paths to the groundwater? And so what we're doing is to take our airborne EM or our TTEM data and develop very simple binary models. So we divide the subsurface into either no flow or flow. And just intuitively, more coarse-grained material water can flow through, more fine-grained material water can't flow through. And so we have our 3D model that's mapping out where we are in terms of coarse-grained material, somewhere between sand and gravel and somewhere between clay. And we now want to impose on that. We want to define them as either flow units or no flow units. And when you do that, it's a judgment call. And so we're working very closely with groundwater managers and growers in how to think about making that decision. And very often, we as scientists have our computational work, and we're making decisions all along the way that's impacting our final prediction in ways that we sometimes don't account for or communicate effectively. So here, this is a critical point where a decision you make is impacting your result. So for example, if the risk is you could not tolerate water ponding at a site, this is an almond grove, and if water ponds here, it's a disaster, then any amount of clay, the moment I have any amount of clay, I say that's a no-flow unit. And so I am then biasing my system to have very few flow spaces, but I'm very confident the water is going to flow there. Another type of risk is I am so desperate for water, I cannot risk missing an opportunity to recharge. And so I'm only going to define a no-flow unit as one that has a lot of clay present. And so then I'm not going to miss any pathways, but I could end up being overly optimistic about recharge at a site, and you communicate that. So what we do then is develop no-flow flow voxels, and then we locate potential area for surface spreading, start your water at all the surface locations, and then we've been using a Connell solver or fast marching algorithm to figure out how long's the pathway. If I start here, where do I have to go, given that I can only travel through the flow voxels to get to the water table. And as you can see intuitively, the shorter the pathway, the better the recharge site. And so we come up with a plan view map that's mapping out path length. And the red is the recharge. Wait a second. Average path. Uh-oh, the color scheme's backwards. We have been going around in circles on color scheme. At first we had red because it's bright, recharge here. And then we said, no, it doesn't make sense. Blue should be recharge. Anyways, all to say red, oh yes, red is right actually. Short path length, yes. Short path length, red, these are the areas where you want to recharge. Blue means you could get there, but there is the risk of ponding, very long path length. So what we have now is this entire computational workflow where you bring in your data, you convert it to coarse fraction, and you come up with a plan view map of recharge here. So what we're doing, we're building a web-based app. FastPath is what it's called. I'm working on the logo. This is so people throughout California can work with this incredible database and analyze the airborne EM database, analyze data from their area, and figure out where to recharge. Because if you have other winters like this, and you have flooding like this, people really want to move this water somewhere, but right now they don't know where. And so the title is actually the title of a project, Harnessing the Power of Geophysical Imaging, that's funded by the accelerator. So we just became a new school in September, the Stanford Doerr School of Sustainability. And a fantastic part of this new school is the support for the banner over my door, I always say, is knowledge into action. I really love taking the research products that we develop and getting them out there, making them usable. And so this was funded by the accelerator. The call for proposals came out last May, and you could get $1 million, but you had to commit to being done in a year. So I'm exhausted. We got one of them. And we are partnering. The main thing we are spending our money on is partnering with software developers. Because as academics, we can take it so far, but we can't make a robust web-based app, which is what other people need. So we're working with Rowan Cockett and Steve Purz at CurveNote, key players in this, Sagi and Meredith. We've got collaborators throughout California. Paul Godwin, who's the Deputy Director for Sustainable Groundwater Manager, is a co-I with me, and Mike Lepick from Stanford, who works on online course delivery, water managers, nonprofit groups, and what we're doing is pulling in all the publicly available data. Because DWR makes this available, but it's actually sort of difficult to access. And what we want people to be able to do is they can go in, we've got an interface, you draw the area you're interested in comes the airborne EM data, in comes all the well data you need, and you work through the algorithm, you make various choices, and you come up with a plan view map of your area. Recharge here. So I have to say, I am beyond thrilled at having the opportunity to do something like this. Like, this is my knowledge into action dream, that we can take all that we've done. Yeah, we have this web-based app now, and Stanford's providing the compute resources. The database is on Redivus. I get a terabyte, and I've been told if I use it up, I can have someone else's. And what we're also doing is developing online training for use, which we've discovered is really critically important. So we're creating this course, working with the Stanford Center for Professional Development. This is allowing us to use geophysical data to find these coarse-grained pathways that we can tap into for recharge. But there's more we can learn from nature too, and that is figuring out where natural recharge is occurring. So natural recharge, you would think, is going to occur where you have these coarse-grained pathways, but there's preferred zones for recharge, and that's very much tied into the source of the water. In California, as I've said earlier, snowmelt in the Sierras is an incredibly important part of the whole groundwater puzzle in California. Snowmelt in the Sierras moves water into river systems, which then moves below the ground surface as the rivers move out into the valley. Snowmelt in the Sierras also moves water directly into the groundwater system of the Sierras, and from the Sierra groundwater system into the groundwater system of the Central Valley. Well, understanding the location and magnitude of this recharge is really important as we think about a statewide strategy for recharge. We could utilize some of these pathways, or we could think strategically, okay, nature's got this covered, we'll work over here. It's also incredibly important as we think about climate change. Like, this is the source of so much of our water. And as we're going to change the timing and amount of snowmelt, what's the impact that's going to have on this recharge? Well, we don't understand at this point. How much water moves through this pathway? How much water moves through this pathway? How do various aspects of that entire mountain valley aquifer system depend, or how are they impacted by climate variables? So this is what we're trying to study. So I showed you this InSAR deformation map of the Central Valley. What we want to use InSAR for is not just to look at long-term subsidence or long-term deformation, but use it to monitor changes in the groundwater system. So use the deformation measurement at the surface here to tell us what's going on in terms of water levels, measured in terms of head in the subsurface. As I've said, if you drop the water levels, you drop head, that can cause subsidence. Well, similarly, if water levels go up, that can cause uplift. So where recharge is occurring, where water's moving into the system, we should see uplift. The reason for this, we are changing at various levels within the aquifer system the effective stress in the pore space. And the effective stress changes the amount of compaction that's occurring in the pore space. If we change the effective stress through a change in head, then we can get compaction, a change in the thickness B, related to the change in head. So pushing water in pushes the clays or grains apart, taking water out moves the grains or clays together. So deformations linked to head changes. Something that's important to keep in mind is that not all zones in the aquifer respond in the same way when it comes to head. There are parts of the aquifer system that are described as unconfined. They have hydraulic connectivity to the atmosphere, to the ground surface. There are parts that are confined, so there's no pressure communication between the water and the atmosphere. When I take a certain volume of water out of an unconfined aquifer, the change in head is given by this equation, the volume of water divided by the specific yield, which is about 0.2. Now, if I take that same volume of water out of a confined aquifer, so down below here, the change in head is now divided by the specific storage, which is about 10 to the minus 5 times the aquifer thickness, which is typically hundreds of meters. So you've got a couple of orders of magnitude difference. So the same amount of water coming out or going in has a much bigger impact on surface deformation if the water is coming out of or going into the confined part of the aquifer system. And people for a long time have said things like, oh, materials in the unconfined aquifer don't compact. Yeah, they have the equivalent potential to compact. We're just not changing the head as much. And so what we're predominantly going to be seeing in InSAR is related to what's happening in the confined aquifer. So what we get in our InSAR data then, because deformation is linked to head changes, as our head changes over time, we'll see a deformation pattern going down when we pump, up when we recharge, down when we pump, up when we recharge. And this is exactly what Wes Neely did, a publication in 2021, where he started looking at that pattern in the InSAR data and saying, when I see that peak coming in, that's an indication that I'm recharging this system. So he acquired, or he used, the Sentinel InSAR data and mapped out these peaks moving from the base of the Sierras out into the Central Valley. And here's his movie where what you're seeing, the pink is the peaks appearing in January, then they move out into the valley, orange is July, then September, then by the winter we're cycling around on top of ourselves again. But it's this idea that you're actually seeing this pulse of water, because we're seeing this pulse in the InSAR data moving out from the base of the Sierras into the Central Valley. And Wes's publication suggested it was recharge. He came to do a postdoc with me at Stanford. Is this really recharge? And why don't we see it everywhere? What is controlling where we are seeing recharge? And so we mapped out the outline to the paper a few months ago, and I'm showing you the initial results. And the paper, I said to Wes, we've got two working titles here. The first is Wes was right, and the second is oops. So still trying to figure out, could this be recharge that we're seeing in the InSAR data? So here's the pattern where we see those intense InSAR signals, and you can see they are associated with rivers, but not associated with all rivers. There's the Kings River. What we have now are airborne EM data. So when I first saw Wes's results about a year and a half ago now, we were about to acquire airborne EM data. Here's our incised valley fill that I showed. So I said, let's fly that bullseye. So we acquired some extra high density lines of data right over one of those locations where Wes is seeing an InSAR signal that he's attributing to recharge. What we can do then is look below the ground surface. So InSAR is fantastic, but realize it's this integrated measurement. There's deformation at the ground surface because of something that's happening below, but we don't really know where that's happening. But if you overlay, there's the InSAR area where we saw that large response, and we have airborne EM data in that area, so we can cut away, and this is what we are seeing in the airborne EM data, right below that recharge bullseye, as we call it. And we can now start to understand what's happening. Here's sands and gravels. This is a confining unit. And so water is actually moving down and getting into this confined part of the aquifer. And if you do the math and figure out the time from here to here and the time from here to here, the hydraulic diffusivity is of the order of magnitude that you would expect. So what we are truly seeing is the signal of water from the ground surface moving deeper within the aquifer system, which is really, really thrilling. And in California, there's lots of shallow wells that can be monitoring what's happening in that top unconfined aquifer, but very, very few deeper wells. And so this says this signal at the ground surface is telling us where we are actually moving water deep within the groundwater system. So then we went to an area where the Kings River comes in here. Why don't we see anything? We know there has to be recharge happening. I should ask you, who's figured out by now why we are not seeing anything in the InSAR data, even though we know there's recharge happening there? Well, you look at the airborne EM data, and what do you see? Thick package of sand and gravel. The finer grain materials are too deep. The water is not getting deep enough to have that confined aquifer type of response. It's staying in that shallow zone. So the water is coming in there, but the pressure isn't changing. And unless the pressure changes, we don't get an InSAR response. So where to recharge? Where is natural recharge occurring? Helps us think strategically about where we might want to recharge. It also helps us better understand what nature is doing. I often say when we're faced with these challenging situations, how are we going to adapt to climate change? How can we better manage our freshwater resources? I always say we need to take a nature-first approach. Let's figure how nature is recharging this groundwater system. Let's figure out where the natural infrastructure is that we can use to recharge our groundwater system. So the nature-first approach also involves using a lot of technology. So I'm a real fan right now of integrating measurements such as InSAR with airborne EM, because again, it allows you to see below the ground surface. Acknowledgements, funding. My last 5 years of my life would not have been as wonderful as they have been without the Gordon and Betty Moore Foundation. So big shout out to them for funding, and then funding from various sources. Local water agencies have been fantastic, California Department of Water Resources, and then the accelerator at the Stanford Doerr School, which has really allowed us to push a lot of the stuff we're doing out there. And while all this happened, students, postdocs, research scientists, many partners, all listed on my website. And with that, happy to take questions. And my voice made it, but I do need a drink right now. Yes.
Water is also electroconductor. What is the role of resistivity of water in your approach?
That's a great question. I flew through the link between resistivity and what's there. So if I had sand and gravel that was dry, it would be high resistivity. If I added water, the resistivity goes down. But the dominant thing we're seeing in these data is clay has low resistivity, not because of the ionic conduction through the water, but because of conduction pathways associated with the clay surface. Clays have a zone of cations right adjacent to the mineral surface, and current travels very efficiently along that pathway. Clays are very high surface area. So a water-saturated sand and gravel is going to be more resistive than a clay. Yeah. Yes?
A couple of questions.
Would you mind using the mic?
Oh yeah, I meant to, supposed to ask. Or I think they wanted you to use that mic there.
Of questions. First question was that are you using a very low frequency sinusoid wave and pulsing it, or is it
It's a time domain system.
So it's a
So
static
not
field
pulse,
which
it's
is
a static,
pulsed?
yeah. Current running through the loop, and then when you shut the current off, that triggers the eddy currents in the subsurface. So.
Okay. And then you detect the...
And then what we detect, so the eddy currents then generate a secondary magnetic field, and what we're measuring at the receiver is the decay in the magnetic field with time over various time windows, and the time windows, early times are from shallow, later times are from depth.
I see. So you're time gating the...
You're time gating,
Yeah,
yes.
okay. Thank you. The other question I had was, once you charge the water, will the ground rise? Or...
Oh, that's a great question. So as long as you're in the elastic, there are two types of deformation or compaction. One is elastic. So if you take the water out, it goes down. You put the water in, it comes back up. Take the water out, it goes down. If you take so much water down that you basically reset conditions, it will not recover. And that point, which you should not go beyond, is the lowest water level ever at that location, because you can imagine these sediments were deposited under a certain condition of saturation, and the structure is formed. Well, then if you go beyond that point, as long as water's coming in and out, the structure stays. But if you go along that point at which they were formed, they collapse. And so once you get below that point, you get irreversible compaction. And that's why there's such serious subsidence in the southern San Joaquin Valley. We're just going down, down. Every year, we're defining a new minimum.
Thank you. Great talk, by the way.
Thank you. Yes. You need to use a mic. I forgot to tell you last time. Sorry. There's a mic right there.
You can use this one. This is on.
Or I could repeat it. You could just, oh.
So farmers already have wells to connect to water. So I think it's in that way, would it be cheaper instead of searching for best depth, best digs, just make those wells by direct explosion like military do, and save a lot of money instead of directing
Instead
your
of
water to
infiltrating,
what
put it-
you found from geophysics. Just making in convenient places where water naturally coming. Would
Okay,
it
so
be cheaper?
you're saying, could we use existing water wells and just recharge there?
Yeah, that's
Yeah.
probably not sufficient, but I even suggest to make the wells by directed explosions.
So you can drill a well. The question is, where do you drill the well? So,
Where the water coming from?
but how do you know where the water is coming from?
But you study natural.
Yeah, but I need the
Movement of water.
geophysical data to do it. So I see what you're saying. If I find a location that's good for recharge, could I just put a well there and put the water in the well? Is that what you're saying? Okay, that is one method of recharge. The reason there's less enthusiasm for that method of recharge is there's the understanding that if you flood water and allow it to slowly percolate down, nature cleans it up. There are these biogeochemical processes that occur that remove much of what could impact the water quality. Whereas if you put water straight into a well, you bypass that natural benefit.
That's why I suggest to make a big wells by direct control explosions.
But even the big wells, you would be taking water from the surface and going right down quickly to deep. And that would be problematic because the time scale that you need to improve the water quality. But all to say, people definitely do that. The concern, you need a totally different permitting structure to take surface water and put it directly into a well. Whereas if you're capturing flood water, people are very willing for you to take flood water and spread it on the ground surface, not put it straight into a well.
So we don't want to eat into the lunchtime too much, no pun intended, but we do have one question on chat.
Oh,
so
sure.
I'll read it out to you.
Sure.
And then we'll make it the last question.
Okay, last question on chat.
Okay, how much, I've got my glasses on, so I'm just going to squint a bit. How much of the Chular, is it Chular, is that how you pronounce it,
Tulare.
lake basin, can efficiently recharge groundwater?
How much of the Tulare? So I've been working closely with Aaron Fukuda, who is the general manager of the Tulare Irrigation District. And I was talking to him 2 weeks ago, and he said 4 years ago there were 2 agents for recharge, which means you are officially allowed to recharge. There were 2 people officially allowed to recharge. This winter, 206. So there are 206 growers who are flooding their fields and getting recharge. Was that the question?
Well, how much, I guess...
How much is available for recharge? Yeah, there is so much in terms of agricultural fields that all it's going to take is growers to have the confidence that it's not going to damage their crops, their land, their almond groves, and they're willing to open it up for recharge. So to me, that's incredibly hopeful.
Okay, thank you.
That's it. Okay.